Okay, good evening. It's 8 o'clock on Thursday, so that brings us to another BPHO Computational Challenge. Again, we have Dr. French here delivering a session, and today it will be on waves and optics. Take it away.
Okay, thank you very much, Professor Chung. Good evening, everybody. My name is Dr. French, and this is Waves and Optics. So if you've been eagle-eyed, you'll have thought, hang on, what happened to quantum mechanics and atomic physics? Well, there we are. That's going to happen next week. So this is going to be a feast of opportunities for computational physics. So we're going to have a little tour of waves and optics, and as usual, I'm going to make some pauses to highlight some various projects, computation that you could do. So if you are new, welcome. This isn't like a kind of how-to session. We're not going to sort of spend ages guiding you through a particular computational paradigm, because all of you are going to be coding in different languages. So think about this as inspiration. And maybe if you want to do some things after this little seminar, is pick one of the topics that you think, oh, I could do that, or that's really interesting. And then look at the notes and then create it for yourself. That's probably the best way of making use of this hour. So let's make starts and welcome. So what we're going to do is start off with the anatomy of waves. So here we go. Here's a wave, starting off with a sort of cosine wave. And let's say the blue one is where we start at time is 0. And the red one is the same wave a bit later in time. So we can think of all waves being a decomposition of sine waves of different frequencies, phases, and amplitude. And phase, if you're new to that kind of nomenclature, is where we are in a waveform. So where we are within a cosine wave. So that's so how many degrees out of 360, or a fraction of 2 pi if we're talking radians, or a fraction of a wavelength if we're talking distances, etc. So mathematically, a wave, which you can break down into sine waves, etc. We can think of the translation in space. Okay, so what I've got here is essentially 2 photographs of a wave, one a bit later overlaid on top of each other. And if you can kind of think about that, this translation of a wave shape, you've kind of got the mathematical anatomy of wave-like phenomena, even things which look nothing like a sinusoid. So before we sort of look at that kind of stuff and some music, etc., here's some sort of mathematical representations of waves. Some of which, if you're in sixth form, you'll probably see all of these. If you're not, some of these may be new. So I think before we carry on, let's just sort of make sure we understand what these are. So firstly, this is the Greek letter for a waveform. So in quantum mechanics, the wave function, but this is really this sort of amplitude, well, not the amplitude, this sort of disturbance. So if you have a slinky, for example, this is the sort of compressions of the springs. It could be the air pressure in the air. It could be the height of a water wave or a strength of an electric field. And that's going to vary with space and time, which of course we can generalize into x, y, and z, or any other vector. So here we've got a cosine wave. A is the amplitude, so the height from the equilibrium to the top, in this case 2. And then what we've got, I'm using radians here. So we could say, well, what fraction of a wavelength have we got? And I'm shifting that by the speed of the wave times time. So so CT is the shift, if you like, of the red from the blue wave. So I'm translating 2 pi x over lambda by that. So yx over lambda, well, that's the number of wavelengths we've got. So the number of wavelengths times 2 pi radians is how many times around my cosine wave have I got. So that's going to be my mathematical anatomy of my waves. How can I go from space and time into a sort of cosine wave? How does that match? So the idea, the wavelength is the distance between the peaks, or indeed the troughs, x and t at time and space. And there we go, there's the amplitude. And phi can be a sort of initial phase shift. So if you think about it, I've not got this starting from 2 here. All right, that would be a cosine wave. I've got it a little bit shifted. So that can be sort of any number you like. And when we're combining waves with things like wave superposition, we can have waves with different phase shifts, and they can constructively add or subtract, in fact. So there we go. In general, we can talk about waves, and this might be sort of a top level view. There's a sort of position vector to a point on the wave. K is the wave vector, which defines the direction. If we're talking optics, that will be a ray, okay? And we can use complex notation to describe this. So if you've not done this, this might look exotic, but this is a complex exponential. That's the imaginary number. And we use something called de Moivre's theorem, which turns that into a sum of cosine and sine waves. So e to the I theta is cos theta plus I sine theta. And it turns out that this is a really nice way of representing waves, albeit it makes it complex, but actually makes the mathematics involving this less complicated, because integrating and differentiating exponentials is a lot nicer than doing that with cos and sine, because they turn into each other with sines, etc. So there we are. So the key idea is that the Fourier components of waves, so all disturbances, can be thought of as sum of cosine waves, which have different amplitudes, frequencies, and phase shifts, and you can just add them up to create any of your disturbances. So understanding this means we can understand any wave you like. So here's a few things you might recognize. There's the wave speed in terms of frequency and wavelengths. There's the period and frequency relationship. And we've got our wave number, which is 2 pi over lambda. And that's how we can turn this one into a slightly simpler version, which is perhaps a little bit more memorable. Okay, but in terms of a translation of a wave, really this is kind of where I would start. So given this is a computational course, what would we do next? Well, hopefully you'd be thinking, let's go and plot this. This sounds like a recipe. Indeed it is. So here we go. This is some MATLAB code. And if we look at the left, this is the kind of how I'm inputting various things. The bits in green are the commentary that tell you what something is. So that's for our benefit. The computer doesn't care, but we do if you want to make sense of your code. And then I've defined various things like sort of the frequency and the period, the time delay, etc. So what I'm going to do, I'm going to go and put that into MATLAB, and you can sort of see how this evolves. Okay, so I'm going to go and sort of swap views to some PowerPoint, and I'm going to go and paste all of this into MATLAB, and we can kind of see how that's going to work. So here we go. Here's MATLAB, and I'm going to go and paste it directly in. Oops, and I have it near it somewhere. Let's just find. There we go. I have. Let's go and do. Not my time units. That should be fine actually. I think we've got everything. Oh no, let's just let's paste this lot in. Time unit. Okay, yeah, my time is literally just for. Oh, I see what I've done. Yeah, I've got my commentary here. I haven't sort of terminated, so so I'm going to copy the rest of this one, and I'm going to paste that in, and hopefully all the variable things should now appear. So what I've got is I've got an array of time. It looks like a spreadsheet. There we go. So that's time between 0 and how many periods I've set. Let's have a look. I've set my times to be, there we go. The number of waves times period, n waves, is 3. So 3 periods worth is my time array. And then I've got x, and this is my sort of, that's my sort of spatial extent. And then I've got my wave height itself. So in terms of what I might want to plot, okay, I'm going to plot sort of, let's go back to our presentation so we can see it. We've got this one here. So there we go. This is slightly smaller, so I'm going to go and put that in here. And I can actually plot my waves. Let's just go and plot this one. There we go. And let's have this one here. So we can see that plotted. There we go. There we are. So I put my plot command. I'm plotting x versus y. So x is my sort of spatial extent, my and y is going to be my various waves. So yx1 and yx2. One is the time shifted version. Okay, so that's what I've just done. And I've added a legend to give it a title, etc. So you can use all sorts of languages to create these kind of things. Matplotlib is very good if you're using Python. You know, there's probably hundreds of different ways of doing it. But the point thing, you can even do this in Excel as well. Yeah, so the idea is once you've got your mathematical recipe, let's go back to our presentation, you can actually sort of plot it out. And I'd highly recommend this. If you see a bunch of mathematics, think, well, how can I go and plot that? Take a bit of time to really understand it. And notice in the corner, I've got a title here. So I've got whatever my inputs are, my amplitude, wavelength, wave speed, and then things I've calculated, like the period here being 1 over f, and the frequency 1 over the wavelength. All right, that can be calculated and put in your title. So everything's kind of automated. So there we are. So the second we're going to do is look at standing waves. So if I've got a wave on a string, like a guitar, now I don't know if this is actually coming across with my camera, but if I just bounce out of this the screen share at the moment, I don't know if you can sort of see me. Where are we? We are back in Zoom. There we go. Ooh, it's got it. So I don't know if you can see this little instrument. This is my little new ukulele. This is going to be used today. So if we've got
if you stop your screen share full stop,
okay,
then you can maximize yourself.
Ah, oh dear. Right, there we are.
Okay, that's perfect.
So there we go. So if we want a standing wave, a nice example, if I get this stationary, is a guitar string. So it's sort of pinched at one end, okay, and also at this end here. So if we have a wave on this string, if I can do a little pluck, my pick out of the way. So there we are, joystick. All right, so that's my that's the top string. So that is vibrating with nodes at either end. Okay, so how can I represent that? That's vibrating quite quickly. Well, this is where we need a bit of computers to do it. So plop that there. I'm going to show my screen again. There we are. Hopefully you can see it. Can we see me all right? Have we returned? Anson, have we returned okay?
Yes.
Oh, fantastic. Good. I had the horror of silence there. So yeah, so here's a little app. For analyzing standing waves, these can be a little bit abstract, even if you've got some nice kit like Slinkies, etc. The fact that they are dynamic. So this little app represents a standing wave. Imagine a kind of photograph using a high-speed camera zooming onto my string. So I've got my nodes where there's no string movement either end of this. Well, this is slightly larger than my ukulele. This is 1 meter, sort of much bigger instrument. I've not put any units on this, but this could be a very small disturbance of a transverse wave on my string. And notice in this case, I've got a node in the middle as well. So what do these colors mean? Well, let's animate this, and that's going to really help you to understand this. So if I just run this little app, okay, so I'm going to clear my screen, and then we go to my little app here. So these are sort of these are done in MATLAB, but the idea is you've got a graphical user interface here, standing waves. And I'm going to run this. There we go. Let's just minimize all of that. There we go. Okay, so there we are. Actually, I think you probably don't want to see my horrifying backdrop. So let's put this in front of it. There we are. Okay. So basically, what I can do is here the green is a snapshot of my wave. All right, in time. So you can kind of think of a wave as a spatial extent, a sort of photograph of a wave, which is what we've plotted here. And if I increase time, what you can see is this standing wave evolve. All right, so the nodes stay in place, the antinodes are the same position, these ones, but everything vibrates in phase. In other words, the time variation is the same at all points along the wave. That's a characteristic of a standing wave. In fact, mathematically, it's a product of a time variation and a spatial variation, which is quite different from a traveling wave, which kind of moves from left to right or right to left. All right, so I think to make sense of this, you've got to actually animate it. And so the sort of multicolored envelopes, which is, if you look at a guitar string, or if you play a stringed instrument, you'll see this sort of bulge. That's because your eyes can't resolve the movement of your string. It's going too quickly. So these little colored lines represent the position of the string at different times. Okay, and that's the kind of thing you'll be sketching in A-level examinations, I'm sure. But I think you need to animate it to really understand what's going on, and we can kind of make time go slower using a simulation. So another way of thinking about a wave is, of course, the time variation. So what these 3 points do is that they correspond to certain spots along the wave. So at x is 0.2, and you can see the red line here represents what's happening versus time. So as I sort of evolve this, well, it sort of plots from where we are at the moment. So I'm nearly at the bottom, and then this is how that spot there would vary in time, going forwards and backwards. And what you can see, as I get a bit closer towards the node here, the amplitude will decrease. So if I move the black one, for example, my amplitude is getting smaller, but of course my period is exactly the same. And there we are, that's almost 0, and then it gets bigger again. Okay, so we can see the time variation. So this is the sort of thing you'd see in an oscilloscope, right? At one point spatially in a wave, how is my wave varying with time? And if I took a photograph of my wave, how does it vary with space? And if we use sort of animation, we can see how that also evolves with time. And just like I showed you in the previous graph, we can have things like the frequency, the wavelength, the period, the wave number, 2 pi over the wavelength, and the angular frequency, 2 pi times the frequency, can be all calculated for us. So we can make a kind of wave calculator. And we can do some harmonics as well. So if we have our fundamental, that's when we have nodes on both ends. And of course, this is it's like a guitar string. Here we are, harmonic number 2. We've got a node here. And I've taken it all the way up to 10, which looks quite pretty. And of course, nodes at both ends are not the only kind of wave game in time. We might have something like an open-ended tube. And if I hover over there, can someone put in the chat quickly, what's my sort of condition? How does the length of a tube vary for if I have an open-ended tube like an organ pipe? So how do the wavelengths relate to the length? Can you stick that in the chat, please, if you know the answer to this one? I'll give you a hint. I'm going to undo this button. Let's have a harmonic number of 2.
We got a 2L question mark.
Ooh, not quite. So it can't be an even number. So what we've got here is we've got an antinode at one end and a node at the other end. So I like to think about this. If, for example, if you're driving this, you've got an antinode of pressure. And this could be air pressure. So the height of this graph represents the pressure in a tube, for example, like an organ pipe, or perhaps even your mouth, actually, if you can think about it in that kind of way. And the outside is atmospheric pressure. So that's got to be a node. So we've got an antinode at one end and a node on the other end. All right, so we can't have an even number of wavelengths. So any more answers in the chat? Then we'll get a bit quick and get there so far.
We got both a 2L plus 1 and 1.5L.
Okay, all right. So yeah, we can generalize. So the idea is an odd number of quarter wavelengths. That's why, because we've got a quarter wavelength from an antinode to the node, and then we've got another half there. So that's 1.5. Sorry, not 1.5. That's sort of that's another of quarter wavelengths. That's 3/4 of a wavelength we've got here. And so if we increase our harmonic number, we can have another next odd number of quarter wavelengths, etc. All right. So that's a bit harder to sketch, but the idea, if you're doing this, say, manually, is you would actually sketch an antinode, node, antinode, node, antinode, node, etc., and then join the dots with these little things. That's quite a nice way to sketch. But anyway, you can see it visually in this little app. So there we are. So that's a nice way of sort of visualizing waves to get your anatomy is a good thing to do. So there we are. So there we are. So 2n minus 1 times a quarter of a wavelength is going to be our length of a wave. And in general, we'd have to add something called an end correction. All right, so the node of pressure isn't exactly at the end of your tube if you play an organ, for example. And a nice model of this, it's about 2/3 of the radius of your tube. So if your tube isn't ridiculously long, quite a fat thing, that might make quite a difference. There we go. So there we are, a little model. So the next thing we're going to do, unless we've got any questions, has any questions appeared in the chat before we move to another little simulation?
They just asked what's the size of your time array for this animation, just for reference.
Size of what?
Time array.
The size of the time array. Oh, right. Okay. So I'm rather arbitrary. I've made a time array, maybe like 1,000 points long. I'd have to go into the code to see what I did. But basically, what you want to do is plot something that's smooth. So when you look at it, it looks like an analog trace. But actually, if you were to zoom in, there'd be lots of little sort of jaggedy peaks there. So something like this, probably 1,000 points would be fine. But 100 points, it probably wouldn't, it wouldn't look smooth. So this is another good reason why you might want to do it in a programming language rather than Excel. Although Excel, if you keep dragging down, can accept about 100,000 points anyway. But that gets a bit unwieldy. Right. Okay. So we're going to record some sound now. So I've been giving this a go, and this is what we call a spectrograph. So basically, we're going to record a signal about 44,000 times a second. This is again another little MATLAB app. I've got right and left channels. It's a stereo recording. And then what we're going to do is we're going to look at the frequency content of this. So every, I think it's 10 milliseconds, we're going to do something called a Fourier transform. And basically it says, what are the sines and cosines that form this wave? What are their amplitudes? And what we're going to do is we're going to plot, well, the amplitude squared, the power, at different frequencies. All right, so we're going to look at all the different cosine waves at different frequencies and see how their powers are given that small bit of time. And this way, we can actually track frequency versus time. So I can't remember if this actually has an animation to it. I don't think it does. So let's go and record one. So there we are, some live science for you here. So we're going to go for sound analyzer. There we go. And what I'll do, I'm going to play a little bit of ukulele for you. Let's make it a bit longer. Right, so I can see Dr. Chung roll his eyes. And there we go. So here's my axe. So I'm going to play some 3 chords, probably, I don't know, a G, C, and a D, something like that. This is a G, this is a C, and this is a D. So I'm going to go and record those and see what they sound like, see what our harmonics are. So there we are, 5, 4, 3, 2, 1. That was a very bad D. There we are. Right, that should be nearly there. Oh, I hope that's not crashed on me. That's the worst chord in the world. There we go. Right, so what can we see? Well, we can see the 3 things I'm playing here. And if I change the frequency of my graph to, say, 4,000 hertz, maybe a bit less than that, maybe 2,000 hertz. There we go. Right, so, and let's set my time extent to be about 6 seconds. So all that sort of rubbish at the end, we don't hear. There we are. So what can we see? Well, basically, we can see a whole bunch of sort of horizontal lines, interestingly spaced. This is because a ukulele is rather a weird instrument, because the frequencies don't go down as I pluck. So the upstring, I think that's a G, is actually higher than the one below it, which gives the ukulele rather its sort of joyous sound to it. But what you can see, it's not just one frequency. You've got these harmonics all going all the way up. If we plot it in time, and if I zoom in, say, at about 2.5 seconds, so if we go for a 2.5 to 2.51, all right, actually, that's probably a bit too much of a zoom, isn't it? So let's go 5.5. There we go. We can actually see the waveform itself, which has got lots of little tiny jaggedy harmonics to it, and these higher frequency peaks. But it's also a sum of different cosine and sine waves. I'll see if I can sort of sing a note to you for a bit, it's like a purer one. Let's go for 6 seconds. Right, British Physics Olympiad. Right, British Physics Olympiad. There we go. So we've got the sort of vocal expression I've got here. So this is the amplitude versus the different times. And if we zoom in, let's go for, again, 2 seconds and maybe 2.05. Right, you can see my my voice here. Let's go for, there we go. There we are. So there's our waveform. And we can see mostly I'm singing at about, what's that, 0.25 kilohertz, something like that. And these are my harmonics. All right, which a bit jaggedy in terms of the way I've been singing here. But there we go. So this is how we can create what we call a spectrograph. So this is really interesting. Very useful in terms of analyzing sound. You know, if you want to look at your voice or detect your breathing rates, all sorts, how your frequency varies with time is a wonderful representation of what's going on. So there we go. So we've got, this is what's been recorded 44,000 times a second. And if you manipulate, this is the essence of all signal processing. And if you want to analyze this, plotting frequency versus time gives you all sorts of structure. Right, so there we are. Okay, so something a bit different. I've got my axe away. We're going to do a little bit of maths now. So a bit of music theory. So since about 2,500 years ago, time of Pythagoras, one of his many wonderful inventions which he bequeathed to the world is this idea of harmony. So a fifth, for those musicians amongst you, is a frequency ratio of about 3 to 2, so 1.5. And this produces quite a nice sound. Often this is a sort of sound using rock as well. And an octave is a frequency ratio of 2. So if you play a C and a C above it, that's twice the frequency. Concert A is 440 hertz. That's what we've defined. And so an octave above that, the next A is 880 hertz, etc. All right. And although it's not quite the same, what we call the modern equitempered scale is actually in terms of powers of 2. So actually, it's a geometric progression. So if I go from, say, an A to a B flat, what I'm doing is I'm multiplying the frequency by the 12th root of 2. Okay, so I have sort of 12 steps in that. If you think about, you go from sort of A B flat, B, C, C sharp, etc. Go all the way, and eventually you get, so that you're increasing n each time. Eventually you multiply by 2 and you get back to A again. So there we go. So that's sort of our equal tempered scale, which is probably what you'll have on a keyboard, but it's not quite right. And if you play a violin, you might sort of say, well, that's not quite the sort of harmonious proportion, but they are very, very close together. It's an interesting sort of mathematical exercise to see how these are related to the sort of actual ratios. Okay, so there we go. Now, if we want to do some recording, so there we are. This is my partner Lucinda playing a violin, and I've got the spectrograph here, the frequency versus time, versus I sort of zoom in on the waveform. So she's playing one note to keep it a bit simpler, which is a concert A on a violin, 440 hertz. So you can see that these are, well, if you do some calculations on it, 440 of these per second is what you get. And you can see in the graph here, that sort of dark red is illustrating the sort of maximum power of my harmonics and my Fourier components, which, given it's a violin, are beautifully spaced. Right, that's the fundamental, twice the frequency, 3 times, 4 times, 5 times, etc. And we get loads. We get about 10 or 12 dominant harmonics. And that's why we get this sort of extra peaks and the sort of raspiness of a violin. It's quite different from other instruments. If we play guitar, for example, it's exactly the same note. We again see our dominant frequency here, but you find the higher frequency ones die off quite quickly. It's just the way the guitar string is rubbing against the neck of the guitar, causing friction. So the higher frequency ones die off much more quickly. It has that sort of plucking sound. So the waveforms look a little bit different. If we play a flute, for example, we are continuously feeding energy in, and you're blowing the flute. It's also got a fixed end, so you have your sort of you don't have the same harmonic proportions. It's an odd number of quarter wavelengths, and you get these much smoother sinusoids here. All right, it's because with the way we're sort of adding up our frequencies, it's more dominant at the fundamentals. Okay, so although you're playing the same note with a flute and a guitar and a violin, they have a much different, a very, very different sound, which means when they're put together musically, that can sound interesting. It's all to do with the harmonics. And there we go. So this is a chromatic scale on a piano. So what Lucinda's doing is basically playing each note, which, if you recall from the previous slides, each one is the 12th root, or 2 to the n over 12, times the previous one. So a power law of harmonics. And you can see that I'm pressing ding, 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 ding on a piano in the way that I'm recording and representing these things. So there's lots of ways of recording music. If you don't have your own little computer program for this, something like Audacity is free and fantastic. And can produce MP3 files and WAV files. And these can be read into Python and MATLAB and other programs. You can usually download various tools which can do that. And then you can literally play around with your disturbance versus time and plot these graphs. That's a really nice thing to do. And maybe you can record your own voice or your own personal instruments. I usually do this with my students at school. I ask them to bring their instruments in and get to play something simple. And the weirder the instrument, the better. I think we had a trombone, which is not particularly weird, but it makes a great sound. Lots of violins. I've had a cello played through a tube of fire. That's pretty good. I haven't had a nose flute yet, or a gamelan, but maybe some of you play that. So there we go. That's the sort of scale. And you can see the frequency is not linear. Okay, we have this sort of power law of our harmonics. Okay, so are there any questions on that before we move to something else?
Maybe the first one. The spectrograph display harmonics of the combined wave, which were decoded using Fourier transform.
Yeah, that one.
Yes.
What would you like me to do about that? Would you like me to talk about that again?
I guess very briefly, just what exactly are we seeing in the spectrograph?
So here we go. Here's my spectrograph. So this is a slightly different recording that I made before. So actually, I think what I'll do, I'll record something. I'll sort of record 2 little things, rather than talk. I'll just sort of sing sort of 2 notes, and we can, or maybe 3 notes. We can sort of see those. So let's go for lucky 7. Okay, and we'll go for a 3-second delay to keep it quick. Let's go for that one. la, la, la. La, la, la. Right, okay, so there we go. So that's what I've done is I've recorded, I've sort of sang a note. You can see the notes that I've sung there with some sort of silence in the middle. And what I've done is every 100 milliseconds, I basically said, okay, let's, if I make that, actually, don't think I can change that. So if I make that, so every 100 milliseconds, I say, okay, what is the balance of frequencies in that signal here? Remember, I'm getting 44 data points per 44,000 data points per second. So every 100 milliseconds, I say, okay, what are if I work that out as a sum of, so this little signal. Let's zoom in actually so we can see. If I go to 1.5 and 1.45, okay. So we've got a signal here. So at that point in time, for 100 milliseconds from the start to the end, I say, okay, if I was to think about that as a sum of cosine waves at different frequencies, you know, from low frequency all the way up to, I think about sort of 10,000 hertz, what are the amplitude of those cosine waves? And essentially what I'm plotting is, it's not the amplitude, but a logarithmic version of the amplitude. I'm plotting as the color scale on this graph at each of those times. So if you imagine I'm subdividing my time in 100 millisecond intervals, and I'm saying, okay, that will give me a vertical strip of color. And the color, it depends on the sort of amplitude of my Fourier components, my various cosine waves at different frequencies. And what that means is you can see how the frequency varies with time. So you can see I'm singing at about, what's that, about 150 hertz, something like that. And then there's the harmonic above and the harmonic above that. So I've got 1, 2, 3, 4, 5, 6, 7-ish harmonics, and it all gets a bit messy. The next note was a little higher, and the next note a bit higher too. All right, so hope that makes sense. Right, okay, let's go back to our little presentation. So there we go. So we're going to have a little look at laser diffractions. This is an amazing photograph, which one of my students took. So I think if you're using, everyone uses lasers at school, and a grating, a piece of plastic with very, very fine cuts made in it. So you get sort of, you know, an interference pattern, well, sort of a diffraction pattern from your light illuminating your various slits. But I think what's rather cool is that rather than just putting spots on the wall, if you get some chalk dust, or even better, a little smoke machine with, I think it's like a sort of silica gel or something like that. It's not very dangerous, but you sort of, it's the sort of thing they use in theatres. You can actually see the laser beams fan out. It's absolutely fantastic. So we had a red and a green laser here. So a little bit of theory, which I'm sure you've all met before. So the idea is you've got waves incident on an aperture, which in the case of my slits, if we zoom in, there's two tiny little holes separated by distance d. And the idea is in the far field, so a long way away in terms of wavelengths from your apertures, you can think about the waves arriving in sort of straight lines. And so the path difference between these, you know, the green and the red ones, as it were, is d sine theta. So d is this distance here, and d sine theta is this distance. So when that's a whole number of wavelengths, you're going to get the constructive interference. So there we go. This is what you can write down. And if you rearrange that, that gives you an expression for the angles at which we're going to get these little sort of peaks. So a nice way of representing this is, again, a little app. So you could code this up. And if you were sort of doing this for the first sort of time, and let's just go and run that quickly. So I think we'll quit the other one. There we go. So let's go for, what was it? Diffractor. There we go, diffractor. Although again, it's about, if you can animate things, I think that gives you a lot more sort of sense of how things are working rather than just a static picture. So what we could do here, let's just go for a double slit. This is what we tend to do at school, isn't it? Right, let's go for a double slit, and the slit widths are going to be a very, very small number of wavelengths. There we go. So this is what you might have if you have two slits, and the spacing is 3 wavelengths. So the idea is that sort of you've got sort of sine theta is n/3, or sort of d sine theta is n lambda. And if my slit spacing d is 3 wavelengths, you rearrange that, you get peaks at the inverse sine of n/3, where n is an integer. So I get sort of, that's at 0, that's n equals 1, that's n equals 2, and then n equals 3, we've got at 90 degrees. So this is sort of the angle of my diffraction pattern, and these are the peaks. So the first thing you might want to do is work out where the peaks are in like a little program. A bit more advanced is to actually plot the graphs itself. And I've got some recipes for that if you're interested. But basically, it sort of shows you where the peaks are. So if we increase the slit spacing, we'll find the peaks get closer in, and reduce the slit spacing, and the opposite happens. All right, so we get that sort of dynamic effect. And then what we can do is you can say, okay, if I have the number of slits and that increases, you'll find we sharpen up the pattern, but our grating lobes, the angle we get the maximum, is at the same point. So you can play around with all the parameters of my grating, the number of slits that are in the beam, the slit spacing, and your graph can dance before your eyes. So as a general point, if you have a physics formula, try and code it up with all the parameters, and then you can use things like little sliders to investigate what's happening. And interesting is what happens when the slit width gets larger. What this happens is it produces an envelope, all right, which will initially depress the sort of high angle grating lobes. And eventually, if it's really large, we'll actually start to have maxima at higher angles. So you end up with some quite complicated patterns, which if you want to do a really tough Olympiad question, they probably involve all three of those things. You get to sketch the curves. So there we are. So let's have a look. Let's go to full screen mode. So there we are. So here's a particularly tough pattern. So this is 650 nanometers. This is red light. The spacing's 3 wavelengths. The slit widths are 2 wavelengths in this case. That's not massively a realistic picture I've got there. And we've got 5 slits. And you end up with this quite a complicated ensemble of patterns where you've got your envelope with minima related to your slit width, the maxima related to your slit spacings, and the sort of little ones and the sharpness related to the number of slits. And there's actually a formula which you can derive. That's a nice university problem to work out how this works. So that's actually the blue curve that I'm plotting there. So if you want to actually do this yourself, download this slide and carefully code up this thing. All right, cool. So there we are. That's looking at diffraction and models thereof. And if you want to really go for it, and you think, well, hang on a minute, what happens when I'm really close to my aperture? I can actually just add up the waves. So this is this sort of exponential wave function. So don't worry if you've not met this before, but if you have done this, if you know what that means, essentially we can add up this is this Huygens construction. You can add up little wave disturbances from a big aperture. So essentially you've got a little wave from here and there all the way along, and you're literally numerically adding them up to create your wave pattern. So I've represented it as an integral, but you can actually do that by as a sum. You can make dz a tiny little amount. There we are. In my examples, that's a 500th of my aperture. So it's a bit like I've got 500 ripples emerging all along here, and then how do they add up at this point? So that's something that sounded like a nightmare you used to do by hand. With the computer, you can do that very quickly. Okay, so let's reflect upon something else. So the law of reflection is probably the sort of simplest law of optics. The idea that if you have a beam of light, a laser beam, in fact, could any beam striking a surface, and here's your normal. The angle of incidence is equal to your angle of reflection. So you might ask, well, why is that? Well, there's lots of that. That could open a whole Pandora's box of interesting answers. It may lead you to Richard Feynman and quantum electrodynamics. But a nice answer is Fermat's principle. This is the Fermat of last theorem and all of that, but it did all sorts of good stuff. And basically, Fermat's theorem basically says that the time it takes to get from A to B, all right, is minimized. If we minimize that time, that's the path that light takes. And Richard Feynman would say, well, that's the most probable path, but it actually takes all paths. But that's the one is most likely. So this is a great example to actually do some computation here to show you how this works. So what I've done is I've worked out the travel time to go from A to S, that's our point of reflection, and from S to B. And there's a little bit of maths to do here. You can go through this in slow time, but I hope you can kind of see that I've got a bit of Pythagoras going on. So X is the distance between the sort of upright here, the start of my coordinate system, and my bounce point. And I'm going to vary this, right? So if I make S sort of not halfway between, the angles are going to change, okay? And you can relate the angles by doing some trigonometry. So what you do is you work out the time, and then you say, okay, let's differentiate it. Let's work out the derivative of this with respect to X. That's my only variable. And if you do that, and use a bit of calculus, when that is 0, that happens when sine theta is sine phi. All right, so there's a little bit of trigonometry to do there. And so in other words, when phi is equal to theta. So that's all very nice, but can we see that in a graph? So this is the sort of thing that you would derive on the board at school. But what would be really nice is to actually plot this function, okay, versus x. So I've done this here, and you get a minima, surprise, surprise, when you're halfway between. And there we go, that defines what your path is. So that's really cool. So we can do the same for refraction. And A to B in this case is not a bounce, but we're going to go, towards the normal to S, and then we're going to be refracted, in this case, towards the normal, if N2 is bigger than N1, to B. So I can move my sort of refraction point anywhere along this. So I can vary theta and the angle phi. So what I do, I work out the travel time, just like I did before. But in this case, the speed is different. So the speed of, if it's an electromagnetic wave, would be the speed of light divided by the refractive index. So I'm dividing my distance by my speed to give my time. But of course, the speed is a bit different in each medium. So I'm plotting the same graph, which won't be symmetric in the same way. But the minimum is achieved, and if you can do the same sort of derivative mathematics, is when n1 sine theta 1, or n1 sine theta is n2 sine phi, okay, which is Snell's law, which I'm sure you will be using in your physics lesson. But this is why, and we can work that out by working out our time of flight. Cool, isn't it? So there we are. That's reflection and refraction, and that'd be a nice little project for you to do the maths and then to code that up and maybe make these slides. All right, okay, so now we're going to look at some ray optics. In terms of trying to figure out what happens in a lens, this is the sort of picture that I'm sure you've been drawing for years, that we take two principal rays. So any light rays that go horizontally through a perfect, ideal converging biconvex lens end up going through the focus, some point behind the lens, which is sort of characterized by the thickness and the refractive index and other ways, and radius of curvature. It's called the lens maker's formula. But any lens has a focal length to it, including the ones in our eyes. And there we go. So what you do is to work out where your image is. So this is a projector situation. You take your objects, you go straight through the middle of your lens, and then you go horizontally and through the focus, and that tells you where this one is. All right. So if you work that through, you can actually work out a coordinate transform of going from X to Y to big X, big to Y. So that's the image coordinate, and that's the object coordinate. And so that's a transformation. So armed with that, we don't just have to go from one spot to another spot. We can actually do that for a whole bunch of spots. So what I've got here is a little simulation in MATLAB. Okay, so if I go to code, I go to physics, go to optics, lenses, and we'll go to, say, converging thin lens. So there we go. Let's have Sybil the cat. Sadly, she died last year, so she's going to be memorialized in this this presentation. So there we go. For the red spot on the top of Sybil's head goes here through my lens, and I can move Sybil around using my keys. So what I've done, the transformation you saw on the slide tells you where any coordinate of my image ends up. My object ends up in my image. You can see that she's inverted, but also she's slightly distorted as well. Right, and I've done that by importing an array, literally a grid of pixels with X and Y coordinates, and working out where they go, and then color coding them accordingly, which is quite cool. So there we are. So that's that one, and we can do quite a few, in fact, ideas. So that's the recipe and the derivation of our thin lens equation. I'll leave that for another day. So of course we can do the same for a magnifying glass. And then we have an upright, enormous cat here, which is a virtual image. We can tell that because our observer will be this side, and the rays coming out seem to be coming from this point. That's the apparent source of light. Okay, so that's how a magnifying glass works when our object is within our focal range. But this is, I think, the best example. So this is a reflection in a concave mirror. Now, you might be able to do this in a spoon, but I think that's quite hard to do. So you somehow need to get yourself a concave mirror. And we're very lucky. In my school, we've got this thing, which I think might be from an old searchlight. It's ancient, and it's part of a spherical mirror. And what you do is you dangle what used to be a cow The cow seems to have gone missing. I think the cow's gone to the grazing room in the sky. So now we have a dinosaur. And so you have this inverted cow, which seems to enjoy being suspended from a retort stand. And that's quite hard to sort of see here. If you walk about 2 meters from it, amazingly, the upright cow or dinosaur starts to sort of appear before your eyes, so a much bigger version. And in fact, I can nearly capture this now. So you've got the kind of dinosaur, but this vast upright dinosaur seems to be floating in space. And amazingly, it's actually a real image. So how does this work? So what you do is you're using the law of reflection. So the ray comes from, say, a spot, in this case, Maxwell's head, right? Goes through the middle of the mirror and bounces straight off because you're on a normal. And if you go horizontally, it bounces off this point. And there's the normal going through the center because it's a circle. And that angle is the same as this one. So a bit more maths to do here, but you can work out where that point is by working out the straight lines, if you like, of these points. And then once you've got that transformation, you can work out where the image goes. So let's see if we can run that one. Here we go. So if I go to optics, let's go to lenses, actually mirrors, and we'll go to concave mirror. There we go. So let's use the flying dinosaur. And here we go. So here we are. Here's my dinosaur. And the dinosaur is now inverted and ends up here. And so if you're observing, you'll see this upright dinosaur. And if you move it towards you, the dinosaur gets bigger and smaller. It's quite scary. There we are. That's a reflection of a concave mirror. So this will be a great little simulation, but you'll need to get used to how do I import a graphic file and then plot it on the screen, and how do I work out those XY coordinates and convert them to these points here. Right. Let's. Any questions on that before we carry on? Nope. Okay. Rather than a concave mirror, what about a convex mirror? And you can work out, again, you can look at these rays here and where they converge. So basically, you work out the straight line equation for that ray, and you can work out the bit of work that straight line equation and where do they intersect. This is all geometry, and this is the answer. And that allows you to work out, given these coordinates, where our image might be. Now, this is a kind of fun, but it's a bit more of maths there you can look at. I think a nicer way of thinking about this is this structure. Now, I don't know if you've been to the Science Museum, but upstairs in the maths section, there is, I don't think I've got a picture of it, but there's basically like a sort of an ancient sort of galley. It's like a sort of 17th century ship made of wood with sails and that kind of thing, and like the Mary Rose. And it's this wonderfully distorted image. And basically, you've got a sort of like a cylindrical mirror in the center of your image. And if you sort of look in the right direction, you see the galley, which is painted in a very distorted way. It's almost floating inside your mirror. It's a wonderful optical illusion. So what I've done is written a little program to achieve it. So this is Sybil the cat again. What you do is you sort of fit it within a circle. There's an interesting offset to that circle. And then you basically change your array of image, and you turn sort of like X coordinates into angle coordinates. So you'll smear it around. And this is a very good approximation of what we looked at as a transformation in a convex mirror. So there we go. So how would you actually go about doing this? Well, this kind of picture kind of is the recipe. So what you do is you take a photograph and you define a unit circle, and you fit your cat picture, other pictures are possible, inside your unit circle. And then what you do, is you then sort of shift it. So the origin of a new arc is at the bottom of my unit circle. So there we go. And then what you do, sorry, not the bottom, is that little point there. So the bottom of the image, if you like, where the red spot is. And then what you do is that the y extent is going to be the range, albeit scaled in our case by a factor of 3. And the x extent turns into an arc, into an angle within whatever you set. So I've set 160 here. You could be 360 in this case. So you sort of map the grid of my cat to a sort of sector grid. And that's a very good approximation of this, which we call an anamorphic image. So there we go. So there's me, some shades on. And you can see I've done this on a sort of tablet PC. So, and this is a piece of curtain pole. So a really cheap piece of shiny metal. So you can sort of stretch your image so your curtain pole fits within your circle. and then you have an anamorphic image. Of course, if you run this program, you can use any photograph you like. So there we are. That's Fear and Loathing in Port Merion, which is a very strange place in Snowdonia. So I think we've got just a couple of minutes left. Let's go and pick just maybe one more things. I think we've got a bit of Doppler action. Yeah, let's do this. So the Doppler effect, let's go find the right place, is this one. So this is where, you know, your sort of source of waves is coming towards your observer, and you will find a frequency shift. All right. And now, why is this? Now, this is a great simulation. I'm afraid I didn't do this. It's from O Physics. It's a wonderful website, and it gives you all the kind of information you need. And so you're going to kind of see that the waves are kind of catching up with the observer. So how might we actually do this? So there's a few pages of sort of maths here which you can have a look at in general, but I'm going to just show you this one thing. So let's go for this one. So what you do is you've got the idea. These little sort of coloured spots are points in time. So like maybe this could be every second or millisecond, whatever the time interval is. And the idea, imagine if you had a sort of I don't know, a little drone going over the sea and dropping a stone into a lake every sort of every second, something like this. And so what you see is that, so when you started at the sort of dark one, by the time you've got to this position here, these are the ripples that are produced. All right. So as we go along, we're at this point in time now. The ripple from the first one has got to where the brown circle is, and we haven't got a ripple from the really dark blue. The previous blue one, that's where the ripples got to. So we've got these circles which are expanding in radii, but their center is moving with the thing that's dropping the stone in the sea, that kind of thing. And that's a really nice visualization of the Doppler effect. That's exactly what's happening. You're producing sound waves or waves or any form of wave as you move. And so if our observer's here, you can see that those waves are bunching up. And if you're over here, you can see that those waves have an increased wavelength. In fact, you can actually work it out from this formula here, where theta is the sort of angle that we're crossing. So in this situation, theta would be 0. So the ratio of the wavelengths is 1 plus the ratio of the speeds. So that's the wave speed, and that's the velocity of my observer. So that's a really nice thing to plot and get your head around the idea of the Doppler effect, which you might look at from, say, from mathematics, like this one. So, for example, the Doppler shift is the ratio of the speeds times the frequency. So that's all really nice, but can we visualize this? This is a really good thing for you to plot. And just to end, we'll look at what happens when we go faster than the speed of waves. And this is called Mach's construction. This is Ernst Mach, 1838 to 1916. And so how does this work? Well, it's the same idea that we sort of we're creating disturbances, but in this case, we're moving faster than the speed of waves themselves. All right, and we call that ratio the Mach number. So Mach 2, all right, is when I go twice as fast as the speed of my waves. That could be, say, the speed of sound and air. Now, what you'll notice is we get a shock front here. All right, so beyond this, the disturbance hasn't got to us. But we can actually calculate that really easily with some trigonometry. So if you think about it, we've got these sort of circular waves. And if our wave speed is c, in t seconds, our waves got this far. But remember u is bigger than c, we've got this far. So our shock front is going to be a tangent to that sort of circle. And you can see it's a tangent when we build this up. So what we can do is a very simple trick that ut sine beta is ct. And so we can cancel our t's here to work out the angle of my shock front, which is the inverse sine of 1 over our Mach number. So the faster we go, the smaller that angle is. I think I might have some illustrations here. So there we go. So at Mach 10, or a sort of hypersonic missile or something like that, we have a very tiny angle of about 5.7 degrees. Whereas if we're actually going very close to the speed as a Mach to sort of Mach 1, then our angle gets closer and closer to 90 degrees. And that's why we get our sonic boom, because if an aircraft comes past us, we're going to feel that shock wave. Whereas something going very fast, you might be a little long time before you might be well past, because that angle is going to be tiny. So there we go. So a whole bunch of stuff involving waves and optics. And most of this is about a bit of mathematics, either geometry or the anatomy of waves, or even down to spectrographs and Fourier transforms. When you've learnt some wave theory, it's very visual. So get the skills to plot those things. And you can do it in Excel. I think I've got an Excel model of the Doppler shift. There we go. So you can see lots of numbers here, but these are literally the different colored circles that I plotted. This is a situation for Mark 0.8. So a bit of a project to do it in Excel, but worthy, because you're not learning anything new in terms of the physics, but you're really trying to understand everything in your equations and what it means in order to get your visual representation. And I can't emphasize enough that this is an excellent skill that needs to sort of add to your algebra and problem solving. Okay, so I think that's probably quite enough today. Do we have any final questions before we finish?
Yes, so a couple ones which only you can answer. So question one is, where did you learn how to sing? Do you have any tips?
I don't know if that's irony, but oh well. I think that's a bit of a self-taught thing. But we do have a science show, so that's I probably could put a link in the chat. But yes, we do something called Sing a Song of Science at our school. We're sort of going on a brief tour, but we have songs about mechanics, the evolution, the astrophysics, you name it. But there we go. Any others?
Next question is, where does the not horizontal line come from? How do you know the angle it goes into the surface? So I suspect this is from the refraction bit.
Oh, right. Okay. So let's have a look. If we go back to refraction, so this one possibly. So the idea, again, I hope I'm answering the right question here. So we're going from A to B, but in this case, through two different media with different refractive indices. So the idea, so when we learn this at school, right, we tell you it's proof by intimidation, and we say, right, Snell's law exists, and we can use that. If we know the angle of incidence, we can calculate the angle of refraction, or similar problems around using this formula. And so we're saying, okay, well, maybe that's not true. Okay, let's look at all possible ways we can get from A to B, including the straight line way. Okay, so where the angles are the same. So what we can do is, by moving our sort of point S here, we can map out, well, pretty much any possible angle we can think of going from A to B. And that's what I'm doing. So I'm plotting the travel time going from A to B versus that. So if you imagine, I'm afraid I haven't got an animation to drag that point, but you can imagine that sort of a refraction point is anywhere along this line. And the point where the time is minimized is when the angle of incidence and the angle of refraction are related by Snell's law. N1 sine theta is N2 sine theta phi. Okay, any more questions?
And this one is potentially a can of worms. How do I get started with coding?
Oh gosh, right. So the simplest thing you want to do. So let's assume you're doing it because you want to get better at physics. So why don't we do this? What's probably the simplest simulation? Well, actually, maybe a Snell's law calculator could be good. I don't know if I can find this quickly, but how about this one might be a good idea. So if we go onto my website, where is the eclectic one? Actually, I'll put it into the into here. Let's go for that one. Okay, I'll put this in the chat as well. So the idea first is you don't do any coding at all. Is that you write down a mathematical model on paper. That's really what you want to do. But I've got an Excel in physics course, which I'm going to put in the chat. If I do that quickly, let's have a look. Let's go to the Zoom. Let's go in the chat. Is that the right place? I think, Nina, if you can put that a nice place, if that's not the right one. So the link is there now. And what we'll do, if we just go back to the web, there we go. So this is a sort of course that you can download everything here. And a sort of simple calculator might be quite nice. I don't know if I've got that easily accessible. Integrate block, that's intriguing. I don't know what that means. There we go. Let's not do that. Anyway, I've got some. The illustration is not a very good one, but basically we've got a sort of calculator here. What does that do? What does that do? No, it's not allowing me to download it, annoyingly. I might have to change this. But yeah, so you've got an Excel sheet which is basically converting things, distance and time. And then you might say, okay, maybe let's plot something like that Doppler shift, or perhaps the path using Snell's law. So you sort of build things up. But either way, you've got some maths here, and then you want to represent that in code. So I guess maybe a nice one might be this, in fact. So the thing we started right at the beginning is we've got an equation for looking at these waveforms. Well, why don't you code that up in Excel? You could plot, you could have two. You could have one where t is, say, you know, some sort of parameter at the top, and the other one is t is 0, and that's the blue one, and then the red one is overlaid upon it. You know, that'd be a nice half-hour work in Excel, trying to plot a graph and overlay those, and then try and do it in Python or another language, and then it builds. And eventually, you might be, you know, you're keen to sort of write some apps. But that's you know, that's sort of that's not the first thing you do. Any more questions?
I think we're good for today. So
Thank you. Go for it, Dr. Chung. Yeah.
Okay, see you next week, everyone.